My name is Saskia, and I work in the Sherman Parkinson's Research Lab. So I thought I would start today by kind of explaining what Parkinson's is. I'm sure you all are familiar, but maybe not the details. So it is the second most common neurodegenerative disease, and it is affecting 1.5 million people in the US alone. It leads to motor deficits as well as cognitive decline, but we don't know what causes that. We know what leads to the symptoms, but we don't know the underlying factors. We know that genetics play a role, and we know that the environment plays a role. For example, pesticides. But what we do know is that these symptoms are caused by a loss of dopamine in the brain, specifically deep within the brain, down here in the substantia nigra, is where dopamine-producing neurons collect or aggregate, and then they project into the striatum and up here into the frontal lobe, where they release their dopamine. In Parkinson's, the cells in the substantia nigra begin to die, which means there's a loss of dopamine. So this is what a normal substantia nigra would look like. The brown being neuromelanin, which expresses within dopamine cells, and down here, this is what a Parkinson's patient's substantia nigra would look like. So the cells are dying, leading to these symptoms. So what are the symptoms? You guys are probably very familiar with the fact that Parkinson's leads to tremors, but it also causes instability, sloped posture, so they're hunching, as well as bradykinesia, which is a difficulty initiating movement, a type of rigidity. This isn't the most extreme case you'll ever see, but you do see classic tremors in the hands. You do see the short gait, which is the beginning of bradykinesia, as well as when he turns around, you'll see a masked facial expression, which means he kind of has this blank stare. Because Parkinson's not only affects your limbs, but it also, you lose motor control of your face and neck, which doesn't even include the cognitive decline like dementia and depression. So what can we do about it? So what can we do? We can only treat the symptoms right now, the gold standard of which is a drug called levodopa, or L-DOPA, which is a precursor enzyme to dopamine itself. The reason we take oral levodopa to treat this is because dopamine cannot cross the blood-brain barrier. Once levodopa crosses the blood-brain barrier, there it can be converted to dopamine, which is great. It treats the symptoms, fine, but it's temporary. Roughly 5 to 7 years after the start of treatment, patients will develop a side effect called levodopa-induced dyskinesia, which essentially is the opposite of bradykinesia, which is rather than difficulty initiating movement, they have spontaneous loss of muscle control, which many patients say is as or more debilitating than Parkinson's itself, which then leads to deep brain stimulation. After a few years of levodopa treatment, patients can go into deep brain stimulation, which is essentially an electrode that is implanted into the brain, into the motor control regions of the brain, which is connected to a pulse generator that's either implanted in the chest or the abdomen, which sends electrical signals up back into the brain, which kind of regulates the electrical connectivity within the brain, can treat motor symptoms, but not cognitive symptoms. So what do I do? So like most Parkinson's labs on this campus, in this country, we're just trying to treat Parkinson's itself. There are treatments for the symptoms, but there's no treatment that is stopping the decline of dopamine. So the project I'm working on, we're using a genetic model, so a genetic rat model. Essentially, the genetic knockout leads to a slow progressive loss of dopamine, mimicking a familial form of Parkinson's. We're using a novel therapeutic agent, essentially a drug, that we inject into these animals, and then we perform motor function testing month by month. And then, so we compare the knockout model, and then the knockout model with the treatment. And then the next step after that, we sack them, section their brains, and we look at their substantia nigras. This is kind of just an example. We've done the motor testing, but we haven't quite gotten there yet. But this is an example. So all the blue dots are tagging neurons. The brown is tyrosine hydroxylase, which is essentially a precursor to dopamine. So the brown would be dopamine-producing cells. Once we compare these two, we can see whether the effects, so it's called serology, cell counting, we can see whether the positive or the improved motor function we see in these animals is due to a neuroprotective effect or a neurorestorative effect. Neuroprotective would mean that compared to the Parkinson's rats, the treated animals would lose less cells, so there would be more cells. We're preventing the cells from dying in the first place. And neurorestorative would mean that the same amount of cells are dying, but due to this improved motor function, we know that the cells are upregulating dopamine. They're compensating for the fact that there's a loss of cells. So once we determine that, we're one step closer to figuring out the mechanism behind that, what leads to this, and therefore one step closer to a cure. Thank you.